we go. So let me record. All right, we're recording here, and I'm going to turn on the share the screen. All right, so here we are, Tuesday, the 19th, day before inauguration, and class number 9. And let's see if there's any kind of announcements going on. All right, so on the calendar, well, every Monday we show the calendar, see what's going to happen. And I don't normally pull out the calendar the rest of the week, but on Mondays. So last week, looks like that's what we were doing. The 4.4 key was posted over the weekend. And then this week, so I'll break it up into last week, this week, and then the 2 weeks following, like what's coming up. So this week, I did post the keys yesterday, I think, or Sunday, to all the practice problems, the 6 practice problems, the first set. Tonight, you're going to get the second. Well, you already have them right now. They're already available. These are available through the Facebook group. This is problem number 7 through problem number 15. And they're also, I made PDFs of it, and I'll show you that in a minute. Tomorrow, I think we moved. I'm going to double check the weather. I think I moved the air rocket launch. It's a little bit nicer on Thursday. I'm mostly worried about first hour and wind. So probably Thursday, but that's okay. Tomorrow we'll move on. We'll come back. We can do an air rocket launch anytime. So this will grow. Remember, this will change. I'll add to this tonight. I'll put tonight's homework on there, and then we'll update it. Looking ahead for the next 2 weeks. For the next 2 weeks, next week's the big week, for biggest week of the semester so far for us, because that's test week. They have kind of penciled in for next Wednesday. They penciled in a flex day. My guess is, because we're still arguing about it, my guess is they're not going to do that. And this will probably be the first flex day, will be the 3rd of February. Either way, it doesn't matter. And then also on Sunday, you're going to get your 3rd and final set. I think there's like 5 of them. There's a rule on practice problems. I'm not allowed to give you more than 20. This right here, this sample problem right there, this second set is large, like 9. So you're not going to get a lot of homework this week. You'll get some fairly quick stuff, because I don't want to, you have your hands full with these practice problems. I know a lot of you are already working on them, and because I've had questions, good questions. Rose, I think Rose is in here. She saved the day on the help video I have, because she said, wait a minute, were you V2, V3, what are you talking about? And I tried to explain that a little bit in the somewhere, but in the note, I think, on the YouTube, in the description. But anyway, so that's on there, and keep checking those keys. My job this week is to try and I had help videos set up for those first 5 or 6, and now I don't have any set up, maybe 1 or 2 for the next 9. So I'm going to have to every night try and make a help video, so that, just to help you. I hate just showing you a key, because physics is hard. You look at it, you go, what? Too many steps. So if you can see the steps as they're worked out, it makes it better, I think, right? I'm hoping that's true. So a week from Sunday, the 24th, we're going to get the 3rd and final set. And then the test is, well, we'll have a long Zoom. I don't know if we need that long of a Zoom, and the reason is, I'm going to change this from 9 to 10, because the reason is that you have help videos. If I commit to making a help video of each one of these, then really there's no reason to go to the Zoom on the 26th, because you've already watched the help videos. But if you need clarification on something, then you can come to that, or just show up. And then the big day coming up is the 28th for in-class kids, in-person kids. They take their 150-point test. your virtual test, quote, virtual test will be available starting at 2 p.m. on the 29th, and I will email it to all of you. Okay, I'll just email, I'll put you on the list, I'll email you all. So it'll all go out at the same time at 2 p.m. on the 29th. Will we have class that day? No. There's no reason to have class that day because there was no class. There's no class on the 28th. It's just taking a test. So no new material, but I'm thinking it might take me a while to put the emails together, the emails list and all that. So I'm saying 2 p.m. by at least 2 p.m. Okay, not necessarily at, but by 2 p.m. And then you will have till 6 p.m. So that's 28 hours. Right? So 28 hours to do it, to finish it, to get it back to me. Now, to be fair to in-person students, once you start, this is paper and pencil. Once you start it, okay, I'll put some on my front porch. If you don't have a printer, I'll also add some in the handouts box in the front porch. More about this later. But once you start it, you give yourself 1 hour. It's kind of like when you run a movie, you got this many hours to watch it and you got this long before. But once you start it, you got to give yourself an hour, and then you got to be honest. And then you finish. Even if you're not done, you say, okay, my time's up. And then you bring it to me. This is the one of the few times you're going to have to bring me. If you cannot leave in your car, say you don't have a car or whatever, you can't ride your bike, whatever, it's bad weather, then you can PDF it to me, send me a PDF. More about that later. Okay, and then February, the first week of February is very busy, but you can read that stuff later. Okay, now on this test coming up, speaking of these practice problems, there will absolutely be no surprises. On a test, remember I can always hold back 10%. I can always hold back stuff and just kind of throw it at you and see how you do. I will not do that. I want to reward you for the effort you're putting in. If you're working on these practice problems at home, you go, man, I'm doing this, I'll get credit. Yeah, you do. You get credit on a take-home test. Rather than getting 10 points, you're going to get 150 points. And then you will get credit because your volume of notes will go up. And so you're going to get two big rewards. One, the test, and then one, the note credits you're going to get in February when you turn in your packet. So yes, but it's delayed. It's a delayed credit. That's the way it is in college. So also want to point out that I do have these by request. I do have PDFs of these questions. They're all kind of on one. They're all combined into 1 or 2 pages, but there are PDFs. So if you don't like to go to Facebook and capture it and then just go to the PDF module and then you click on that, then you can print those out. Okay, print out those pages. If you want, it's optional, but it's hard to handwrite graphs, Okay, enough for housekeeping. We didn't do any dogs today. There was no going around. Here's the issue that Rose brought up on problem number 1. She said, I watched that, or she didn't say it, but she inferred that she watched the video. It's only like 54-second video. And she said, I get it, but my problem was I was saying V3 and I meant V2. So V2, like your V2 here, you're supposed to plot it. And this isn't going to make sense to you until you watch the video, until you think through it. That's why you definitely want to do the practice problems, because you're going to come across a problem like this in the test. And if it's the first time you've seen it, you're just going to skip it and say, I have no idea what he's talking about. But that's your fault. You should have watched, you should have prepared. So this first one is, just to clarify this first one's 2, the next one's 4 meters per second, feet per second, whatever it is. The next one then would be 6, right? It's just a pattern. 1, 2, 3, 4, 5, 6. Okay, so that's your next arrow. Then if you drew another arrow at 3 seconds, if you drew that, say the next thing, you draw another one, it's going to be 8, right? 8 long, because see where the acceleration is increasing by 2? It's going up by 2. 2 what? I don't know. 2 meters per second, 2 miles per hour, but whatever, it's 2. These are unitless, so I can put them all on the same graph. So you do it for V, and then you go ahead and show using for the delta Y, you're going to have to use probably the second blue equation to do that, or the second orange equation. Oh, no, sorry, the third blue, or no, because you have time. So it'd be the second blue if you consider A2. So maybe the second orange. I mean, what I'm saying is there is this constant, this is called an acceleration field. It's a core, they're called field forces. So gravity is a field force. It's not just me punching you. It's not just, I'm not just punching a punching bag. It's everywhere, right? Gravity in this room is everywhere. So it's considered a field force. So in this room, there are all these vectors of potential. That's where you get this potential field. It's a potential. If I drop something, it's going to fall and it's going to accelerate with that green arrow. I'm going to lose that as a gift card. That girl gave me a $50 gift card. I'll take that. You know how many gift cards I've lost? Oh my gosh. I find them all over the place. Oh yeah, that expired 5 years ago. I always forget to actually use them. So then that's enough. I've talked too much about that. Let's keep going. There's the new 9. Okay, there's 9 more. And this is on your Facebook group, and everyone has its own little questions that go with it. So there's a blast from the past, but I wanted to give one where the acceleration is negative. There's a good one. That is a challenging question because I know the last couple of years, these have been blue. I think last year was black. It was a black equation last year. So I'm hoping to nip that one. This is the one where you're writing vectors again. Here's one where it's all symbols, like that symbol worksheet 4.4 we did. This one's about launching a rocket, which we'll do tomorrow or Thursday. This one's about launching a rocket using half tau. These are green equations. Those two are green equations. This one's about plotting a graph. If you know we'll get to this more tomorrow too. If you know the function, can you plot the graph? Here from the graph, you have to write the function. Once again, we'll work on that more tomorrow. And then here, this involves damping and all, damping envelopes, which we just started talking about today in the hallway. And we'll talk about that more tomorrow too. All right, so by the time the week's over, we will have covered all that. We did Joke Monday. This is tomorrow, or Thursday. Okay, so now we spent a good chunk of time on this. And I'll post a, oh, actually, this is the cover. This is the cover of the Facebook group. It's one of the better ones I've seen. If you look up, if you split screen it right now and you look up EM spectrum, you'll find hundreds of images of the electromagnetic spectrum. But this is, I think, when it's simple enough, but it does have a lot of detail in there, like it gives wavelengths and all. Okay, so here we go. Now you need your notes. Well, we said last time that crest to crest is a wavelength, and that's lambda is the symbol. Okay, and then the number of cycles per second, how many times it goes back and forth, back and forth, back and forth, that's hertz, that's frequency. So frequency, oh, and if it's electromagnetic waves, those two are connected by a certain velocity. And we talked about this. James Clerk Maxwell talked about this. What is that velocity? It's called celeritas. And what's its symbol?
The speed of light.
Speed of light. So these wavelength and frequency of electromagnetic waves are connected by speed of light. So frequency is given the symbol nu. As we talked about this, you'll see me repeat myself. It's okay to repeat yourself as a teacher on really important topics. If I keep repeating it, that means that the more I repeat it, the more important it is. So nu, and that stands for frequency. And it's just used for electromagnetic frequency. It's not used for I never hear it used in sound frequency, like sound waves. That's called, you know, pitch. Anyway, so frequency for that. And then the way they're related is there's an old joke, um, an old extremely nerdy joke. And the guy walks into the room full of physicists. Hey, they say, hey man, what's new? And they say C over lambda. New is C over lambda. This is the connection. There is speed of light. This is an equation you should just know. Speed of light. This is actually modern physics, physics of the 1900s on. This is wavelength. I realize we're not a modern physics class, but these are in the standards. And this is frequency. So what's new? C over lambda. If your mom or dad is, if they're a scientist, maybe throw that joke at them. They'll appreciate it. So lambda is the length between crests, between peak, right? As I'm going along. So this gives what those lengths are. From crest to crest of a radio wave, an AM radio wave, is the length of a football field. Those get clipped, they're amplitude modulation. And so they get clipped when you go into a tunnel, you don't hear AM radio because sometimes you hear spotty, you'll hear static, but the amplitude is clipped. And so the information on an amplitude modulated wave is in the amplitude. Now, FM radio, the information is not buried in the amplitude, it's buried in the frequency. So FM radio, you can hear going through a tunnel. Because FM radio, its carrier waves are called carrier waves, but its carrier wave is 1 meter. So in the wavelength, and there's FM radio waves in this room right now, typical FM radio wave is about like this from peak to peak. And I can tune in my tuner. I can tune into that frequency and get the electrons to kind of, as they're going up and down, to line up, and then I can pick it up. I can also adjust the tuning some, and that's, you can make your own radio. It would give you a coil of wire and magnet and all. So then you're picking up all those signals that are in the room. TV is about that too. Radar being now we don't really call it radar anymore. It is radar, but we say, in fact, when we first got our microwave, we called it a radar range. Everybody called them radar ranges. And then later, I guess microwave took hold, but that's where your microwave is. So we talked about this in class. So the length between peaks, between crests in a microwave signal is on the order of centimeters. So here's an experiment you guys can do, and film it if you do it. And also talk to your parents first before you do it, because you may end up destroying your microwave. We destroyed ours, one of our microwaves in the room doing this. So here's what you do. You take out the little carousel that turns, pull that out. You take out there's a fan, there's a magnetometer up there, and then underneath there's a fan. And you take that fan out, just unscrew it, unhook it, like I say, talk to mom or dad, unhook it. Then you'd get a bunch of marshmallows, and you put those mini marshmallows, not big ones, mini marshmallows. We used to do this little thing in class. Mini marshmallows, you put them in a flat plastic tray, okay, or a plate, that'd be fine, as big as you can get. And it's good if you can cover from wall to wall, that'd be fantastic. Then you turn it on, and what you'll see is, you'll see black lines start to emerge as it cooks the marshmallow at certain frequencies. And then you start to measure you can measure the distance between the black lines with a ruler, and then put that back in this formula, H equals C times C over lambda, and you'll find that it's about 2450, 2475 megahertz. And that's what the length of a microwave is. In the microwave oven is 24, I'm off a little bit, It's around 2,500 megahertz. And that's what causes water to rotate. That's how rock waves work. So that's what I'm saying. That's 1 centimeter in that scale. And we talked about all this kind of last week. I'm just going back. Okay, so then we went to the hallway. Now, the reason why I went to the hallway is because of Planck's equation. So write this down, Planck's equation. Planck's equation is this, E, and I've probably told this before, E equals H nu. And by the way, I don't say nu, as I said, I think I told you this last time, but because it looks so much like a V, I just make it this. I make it a curly F. That's frequency. That's frequency, that's frequency. Both mean the same thing. Some books use that because students do mix it up with V. So E is equal to H nu. That is one of the most, that's probably the top, it's a top 10 equation of all time. One of the top 10 equations. Without this equation, Einstein couldn't have done his thing. That's a top 10er in the history of equations. Without Maxwell and without this, Einstein would have never had Einstein. So Max Planck really gave us Einstein. In fact, it was Max Planck who discovered Einstein. Nobody else would. Einstein wrote his 1905 papers, which was a seminal year, 5 seminal papers, like it's a watershed event. It changed physics forever. And you know what? Nobody paid attention. Get ready. You come up with something brilliant, no one's going to give a rip. In fact, they'll probably make fun of you. That's what they do because people don't like paradigm shifts. It's very uncomfortable for them. So Einstein comes along and saying this stuff about special relativity, E is equal to MC squared. No Nobel Prize. He did get a Nobel Prize, for photoelectric effect, which came from this E is equal to H nu. Started the idea of quantum, but no response. Now, when you get up here, so here's the point. The energy of the wave is directly tied to the frequency. So these over here are low energy because look at the link. Look how long that is. What a long wavelength that is. That's low energy according to Planck's constant, Planck's equation. Sorry, I'm buffering. Those are low energy. I have wiped out so much material. I'm still buffering. I don't know why that is. This is a low energy here, and these are high energy because they're very tight. High energy waves. So, like people, like this dude in Nashville, right? He blows himself up, blows up his RV, blows up. God, it had to be about the same destructive power of Timothy McVeigh in Oklahoma City. He just wiped out a couple of blocks, blew. One of the reasons why the theory is he was against 5G. He was all freaked out about 5G, 5th generation, right? Well, those are in the microwave range. That's in this low range. No, it's not. It's not killing you, you moron. It's not high enough energy. If that's the case, light would kill us. It's much higher frequency. So it's like, oh no, get away from those photons. So if you spent 10 minutes actually learning physics rather than obsessively looking through your conspiracies, which were founded by charlatans and people who are ignorant as you are. I'm not saying you, but just people. You might not end up blowing yourself up in downtown Nashville. He was trying to destroy the AT&T 5G towers, is one of the theories, which he didn't. It was back online in a matter of hours. But so no, 5G is not messing with your brain. All right. So we went out in the hallway and we were looking. I wanted them. We took slinkies out there, big long slinkies. I have all kinds of slinkies. And I started going back and forth. And a kid, like I said, a kid filmed it, but the film's not ready yet. So I started going back and forth with the slinky, and we developed standing waves. out there, and I will eventually in the comments put some video. We developed standing waves, and so a standing wave is if you're playing a musical instrument, if you play a violin, any stringed instrument, or you play a wind instrument, you develop standing waves in your trombone, in your trumpet, on your violin, and that's where these waves go. These are your notes, right? And you harmonics. Like so what we did was we started off just doing half a wave, and it was real low energy, half a wave. These, by the way, these are called nodes. Node. These are all things we talked about in class. Comes up like this. That's a node. Where it has no amplitude, that's a node. And that's one of those things you're looking for marshmallows in the microwave. Where that marshmallow, you'll feel it and you go, oh my gosh, I wonder if it'd be good to freeze the marshmallows first. Nah, leave them at room temperature. And then you'll notice that, well, these marshmallows didn't even get warm. And then but then look right next to it, that marshmallow, that's hot. That burned it. And back before they used to have put back in the radar range, there was no carousel. There was not even, I don't remember a fan on our first one. So you would have to hit it for about 15 seconds, stop, turn it, hit it 15 seconds, stop, turn it. It was still awesome. It was still a lot better than an oven. But if you didn't, you'd be chewing along, and then all of a sudden burn your mouth, because there are areas where there's intensity. And by the way, on an electromagnetic wave, that's called intensity. How far up and down it goes. We did this as well. Like we made it real intense. We increased our amplitude. This is intensity for EM wave. That's intensity. Like on your phone, you take you have the thing, you do your control panel, then you can push that thing up, make it brighter and brighter. You're not affecting the frequency of it. You're not changing the color. You are affecting just the brightness. Why? Oh, it'd be a lot harder to do because you need there's source there. I'm thinking it'd be cool if you had a slider on your phone that would change the color, from red to blue to green to indigo to violet. But now you're changing the input frequency. That's not going to work. It'd be hard to do. I said you couldn't do it. Anyway, so that's intensity. And then the pitch in sound is the same as the wavelength, in light. That's the color, or whether it's infrared. See, once you get to this point, it's all radar range stuff there. And then for radar, like for radar towers and stuff, radio towers. But then once it goes a little higher frequency, and now we're on the order of, that's 1/10 of a millimeter. So really, really tiny from crest to crest. Then that's where you starts to resonate with your skin, with your organ. The skin's a weird organ, but for some reason, human skin really enjoys that heat. Dogs do too. I got Pepper here with me. She used to, and now she's sort of out of it. She doesn't understand heat anymore. But I have her with me because she kept falling out of the bed, and that's not good. She can't see where she's at. She doesn't know where she's at, so she just walks off the bed. So I have her in here with me. Oh, come here, Pepper. So Pepper used to, poor thing, she's all skinny because she eats, but she's losing all her muscle. So it looks like she's skinny. She's 18 years old. But Pepper used to just love the heat. Now she just for some reason, doesn't really feel it. But the heat is because it vibrates those molecules, right? Just at that frequency, at 1/10 of a millimeter up to, around there, about a millimeter or so, 1,000 nanometers is a millimeter. So you still feel that as vibrating skin. It feels warm. And then if you go a little higher in energy, you crank it up a little bit more, like on your coil stove, you crank it up a little more. Now it goes from heat to actually red, because E equals H nu. Frequency goes up. I crank that energy up, makes the frequency go up, and then your eyes then start to pick it up as red. Really hot stoves would go to yellow or orange. Orange would be whoa, stay away from that stove. but industrial stoves, orange, you know. And then someone was saying, well, what about like Predator? Because Predator in the movie Predator, you know, he sees infrared. And I said, yeah. So what that says about Predator is that and this is true for any kind of alien race, alien societies, probably somewhere in here, you're going to have most. I can't imagine something growing with gamma rays. You know, no, maybe X-rays. I don't think so though, because you just can't. You can't fit together the molecules. The electrons won't stay in their place. I mean, you can't make your bonding. You can't have your cell walls. So organic life that is carbon based and maybe silicon based or something, but can't really handle anything beyond this range. But you do have alien races that have different stars than we do. They don't have the same. Their sun is not in the same main sequence like ours is. So maybe it's a dwarf. Maybe it's a white dwarf, and so they're going to have a lower energy on average. So maybe they, being low energy, maybe if you had a dwarf star for your sun, maybe then you perhaps would have evolved to see more infrared. I mean, I'm just spitballing here. You it's like Predator, where Predator sees heat signatures, right? So it's hard to hide. If you had maybe a higher energy sun or star, you would be in the ultraviolet, so you could see things in ultraviolet. So this tells us a lot about, you know, if we do find an exoplanet that we think there is life on this planet, we're going to look and see what does their star look like. So should we be communicating with them through electromagnetics, but and probably still radio waves. You need radio waves to go long distances. So it'd be radio waves, but what will they be like? That would be something. Okay, let's ignore the rest of this for now. So I'll have a wave generator, and it's back in my back room. I'll find that and I'll get that out. And then with the hallway thing, watch for the video on that. Okay, people are asking what is H. And so I have this. This is H.
Planck's constant.
Yes, thank you. Planck's constant. And so I have it here. It's a really, really tiny number. You're not going to memorize it for me, but you will probably to about 5 siggies. It's easy, 66262, right? So it's 6.6262. Easy to remember. And it's thing is though, it's times 10 to the negative 34th. Now, I know why Miranda knows it, because she probably used it in AP Chem some, because you do, like the further you go in chemistry, the more you go, wait a minute, is this physics or chemistry? They kind of blend together, physics and chemistry. And part of that is around Planck's constant, because that's when you're looking at electrons jumping around, right? There's no coincidence that the electron was discovered in 1897 by J.J. Thomson, and Planck came up with Planck's equation in 1900, 3 years later. I mean, that's where we were physics-wise. A very exciting time. So the H there is Planck's constant, and just realize it's a really tiny number. So E is the energy of a photon, but any particular photon has got basically no energy. You need billions and quadrillions of them, and then you can start to, you know, impact things. Let's dip onto here. All right. So I want to spend the rest of the time doing this right here. So this is 4.5. And when I was in high school and college, I never understood the connection. I didn't have internet. All we had were books. And I couldn't find it. I went to the library and think about this. I could not find a book that, and the professors back then wouldn't give you the time of day. So I couldn't find anybody to explain to me, how does circular motion compare? Why am I doing sines and cosines, which I understood that pretty well, to explain circular motion? All right, so I guess it's kind of become an obsession of mine that I want my students not to go to college not knowing this. So I'm gonna force you with a pencil and a ruler, no calculator required, but this is a very slow moving. This represents on 4.5 a very slow counterclockwise moving boss. Remember, it's called a boss, going round and around and around in a circle. Perfect circle, not an ellipse. Perfect circle, round and around and around. And we're supposed to, like I have a wheel in my room that I turn all the time. So when I turned it today, really slowly. So it takes it 20 seconds to go all the way around. Okay. So omega in this case, omega is 2 pi radians, right? That's one complete revolution in 20 seconds. And so that is that's 0.1 pi, which is really slow. It's like you backing up your car extremely slowly. It takes you 20 seconds, to go. I don't know what your radius is, but just to get one revolution of your wheel. So maybe 2 or 3 meters. Okay, so let's inverse seconds. So that's our omega here. By the way, and we're running out on time, but remember to show that omega, you show it at the center. You show omega at the center. Now, someone tell me, would that be a dot or a cross? Would it be an X or a dot? For the zoom point, X or a dot?
Dot.
Because, think it as a zoom point, because it's a counterclockwise rotating, right? And so it's counterclockwise, the omega vector is coming out of the page. If you can see my video, coming out of the page up towards me. So that's my omega. Anywho, so what we're going to do is every 1 second, I want to plot the position of that boss. So as I'm going around in my circle, I'm going to get 5 seconds. If it's 20 seconds to go around, 5 seconds for a quarter way. I'm going to plot 5, and I do this in pencil, trial and error. I'm going to put 5 dots, and those dots have got to be equidistant between them. Well, 4 dots actually, because there's the dot here. So split up the space between, I don't think I did a very good job. No, that's terrible. You keep doing it, I'll keep working on it. Split up your space so that there's 4 equal spaces. 4 dots there. And I know I should have had this. This is the 3rd year I've been messing with this worksheet, and I see this summer I'm going to have to put my dots in. Okay, fine. And then split this on this right here, this where I've laid it out, split this into 5 seconds. So put 4 dots between the 0 and the 5. Just, it will not be perfect. That's not good. Did a better job in class. All right, let me split it up again. You cannot cut it in half because that's, I guess I could do that and then go equidistant on either side of them. All right, let's do that. Okay, so there's my 4, not the best, but there's my 4 dots here. Okay, now what you do is you take your ruler. You need a ruler. I'll use this. So you take your ruler and you draw, you're going to come up. I wish somebody had done this with me. You're going to come up with this here. Then you're going to come to, that's where it is at 1 second that way. And then 1 second this way. And then you connect those 2 up. Where those 2 connect. Right there. Where those 2 cross, put a dot. I'll make them blue. There's my initial dot. There's my dot at 1 second. Do the same thing for 2 seconds. Doesn't matter which one you start with. I'm going to come across, and then I'll come up at 2 seconds, and I'll connect those 2 up and draw a blue dot there. And again, keep doing this for the 5. How much time we got? We still got 10 minutes. We can get it. We can get most of this done. This is homework what we don't finish. And then do the same thing here. The next dot. Okay, another blue dot. Notice it's curving in. When you do it again, that one's almost to the top. And you come across here. Okay. 270. Okay. Put that blue dot. And then we know there's a blue dot right there when it reaches the maximum. Okay, now take these blue dots and you're going to do a smooth curve through them. Smooth curve. Don't go dot to dot, smooth curve. Thicken that in. Okay. Now let's come down here. That's the y-axis. Now let's come down to the x-axis. And we already have these dots. We already have the dots in the circle set up. Now let's set the dots up here. So I got to divide this up into five spaces or 4 dots down on the x-axis. See where I'm making my dots now? That isn't good. I don't know what my problem is. Let's see. That would be, I could measure it out, but that takes too much work. I'm just trying to visualize it. There's that one, there's that one, there's one there, there's one there. Okay. That's not a bad way to go at it. Okay, so now take these and you come up. And there's your first second, so all the way up to here. And then come down where you were at 1 second on the circle. And 90 degrees. Okay. Okay, do it again for the next one. And the next one, I'll clean this up. I'm just, since I have my ruler here, I'm just doing it all at once. Down like that. Then we come up till we cross. Tedious, isn't it? We're not going to do this the whole time. Okay, there. We erase the bad parts. Okay, now I put a blue dot. I'm going to put a blue dot. And notice it's curving until it ends up here. Okay. Then you connect those dots. Not connect, but curve, smooth curve. Those are your outlines. Smooth curve. Nice. Whew, okay. So big picture now. So that's, notice we're starting. It's not a parabola. Okay, it's not parabolic. But what you have to do now, and then your homework, and I'll let you go a couple minutes early. Your homework then is to continue to do this on the next quarter. Okay, then the next quarter, then the next quarter. But I'll tell you what, if you do the first 2 quarters, then you can just, I'll show you what I mean. I'll be a Martha Stewart here. I'll pull out the souffle out of the oven. This is what it should look like when you're done. So take a look, screenshot that, whatever. But that's what I need to see. It looks like a roller coaster sort of, but that's what I need to see from you. And then this, sure enough, you already knew this, I guess, but in the Y direction, a circle will give you a sign when you just lay it out temporarily, when you show the duration of where that thing was vertically, it gives you a sine wave. When you show where that thing was, where that boss was horizontally, it'll give you a cosine wave. Okay. So someone told me once, I think a math professor said, they said, Asky, you can't, I was trying to do one, they said, Asky, you cannot have a sine wave without a cosine wave. I said, whoa, why not? I didn't get it. I thought, yo, you're just being, but it's true. You can, if I have a sine wave in a circular motion, there is a cosine wave that lags behind, or you can say the sine wave lags behind the cosine wave, but there's a phase shift, right? That's what you mean by phase shift. When I'm at my peak here on the sine wave, I'm at my lowest point what's called equilibrium on the cosine. When I'm at my negative maximum on a cosine, I'm at my minimum or a 0 on sine. And so it's always a 90-degree or a pi over 2 radian lag between one and the other. Okay. So yeah. So we'll talk about that more tomorrow, that part of it. Don't worry about, for now, don't worry about this stuff. We'll get to this stuff tomorrow. This will be Wednesday. Okay, we'll do that Wednesday. Just tonight, what I want you to do is finish your drawing, finish your arts and crafts for this one here. Finish the other 3 quadrants, and then work on, if you have time, try and work on a couple of practice problems, because now there's 15 of them out of a possible 20. Ultimately, your deadline for that is the test, but you know you're not going to work. Anybody with a figure this thing out ain't going to work 20 practice problems in one night. Well, I'll just watch all the help videos. No, what you'll do is you'll confuse yourself, and then you're going to get pissed. Then you're going to give up. So don't do that. You know not to do that. So please do start looking at those, not even 2 nights before the test. Start looking at them tonight. That way when the test comes around, you're ready to kick my butt. That's what you want. You want to be you will be. How often do you get a game plan like this where you're given the problems? Different numbers. I'll switch numbers around. But I am devoted to that student that is working hard at home. I want to reward you. I don't want to be a big jerk. I don't want to give you something that wasn't on there. Some professors do that. You do all this homework and then you look at a test. This wasn't on the homework. I'm not going to do that to you. Now on a regular test, I'll throw a few in there, but I will not do that here. No. Okay. Okay, so we're good. Hold on a minute. Oh, okay. I thought Pepper was being there. So. Okay, so Pepper and I bid you a fond adieu. We will see you tomorrow, and hopefully Pepper makes it through the night. Another night with this dog. All right, see you guys. Look for in the comments, look for some video I'll put. Bye.